Hi, we discuss Module 5 of Computer Aided Design and Analysis. In this module includes the topics finite element analysis, steps involved in finite element analysis, shape functions, application of finite element analysis, stiffness metrics, etc. In this part we discuss steps involved in finite element analysis and applications of finite element analysis. First, what is meant by engineering analysis? The analyst needs a certain requirements while designing and assembling the parts of the product. The requirements are displacement, stress distribution, pressure, velocity, etc. The different types of engineering analysis can be done. First one is experimental method using prototypes. The second one is analytical method. In this method, we solve the mathematical equations and get solutions. The third one is most important method, numerical method. It gives acceptable approximate solutions. The three types of numerical methods are functional approximation, finite difference method and finite element method. The finite element method is the most important and used method in analyzing the problems. First, what is meant by finite element method or finite element analysis? In this method, we divide the structure into small elements and it is called as finite elements. Then the body is considered as an assemblage of these elements. Then the finite number of joints is called nodes. We find the properties at each type of finite element and assembled together to get whole solution. This is finite element analysis. It can be used in structural mechanics, fluid mechanics, heat transfer, mass transfer, etc. Based on the application of finite element problems, there are two types, structural problems and non-structural problems. In structural problems, we get displacement at each nodal point. In non-structural problems, temperature or fluid pressure at each node is obtained. These are the explanation for finite element method in detail. Next is general steps of finite element analysis. This figure shows the flowchart of steps in finite element method. There are three main steps involved in finite element analysis are pre-processing, analysis and post-processing. In pre-processing involves discretization and numbering of nodes and elements. In briefly, discretization means the structure is divided into small number of elements. That is known as discretization. The second one is numbering of nodes and elements. We divide the structure into elements. We give the elements in a number. So, and each element can be divided into nodes. The third step is selection of displacement functions. If we consider a linear function, we solve phi of x equal to a0 plus a1x, and then we can take a polynomial function a0 plus a1x plus a2x square, etc. Next step is define the material behavior. Material behavior includes Young's modulus, etc. So Young's modulus can be find out the relationship between the stress and strain. Next one is derivation of element stiffness matrix, that is K. F is equal to K into U can be determined in the case of elements. Next step is these elemental matrices is assembled together to form a global matrix. The next step is applying boundary conditions, that is gives a boundary conditions end and fixed end and other end points. Next one is solution of unknown displacement by Gauss elimination methods. Last one, computation of elemental stress and strain based on the relationship between sigma and epsilon. Last one is interpret the result. It is the post-processing step. Then we go through the detailed explanation of each steps. First one is step 1, discretization of structure. It includes the art of subdividing a structure into a convenient number of smaller elements. Is known as discretization. The different types of elements are one-dimensional element. This is the example for a one-dimensional element. This first one is two-noded bar element. That is a bar is considered. It can be divided into two nodes. The next figure, it is a bar element and it can be divided into three nodes. Next one is two-dimensional elements. Two-dimensional elements includes triangular or quadrilateral elements. The triangular element, the first triangular element consists of 3 nodes and the second one is consists of 6 nodes. Next element is three-dimensional element. Three-dimensional element includes tetrahedral or hexahedral element. This is the figure for the tetrahedral or hexahedral elements. You must study the figures for examination. Next one is axisymmetric element. And an axisymmetric element is developed by rotating a triangle or quadrilateral about a fixed axis located in the plane of element through 360 degree. The second step, numbering of nodes and elements. The node numbering based on a certain condition, that is maximum node number minus minimum node number is equal to minimum. For example, we consider a rectangular element. The two types of node numbering is available. First one is longer side numbering, second one is shorter side numbering. First we discuss longer side numbering. We consider a rectangular element and it is divided into 13 elements. Number with circle denotes elements. Number without circle denotes nodes. So we give the numbering in longest side. 1, 2, 3, 4, 5, 6, 7, again 8, 9, 10, so on. And we get 22 nodes and 13 elements. 18 elements. We consider an element 3. Element 3 consists of the node numbers 3, 4, 11 and 10. So maximum node number is 10 and minimum node number is 3. Our condition is maximum minus minimum node number is equal to minimum. So maximum node number 11 minus 3 equal to 8. From longer side numbering we get the difference is 8. Next case is shorter side numbering. We give the numbers on shorter side of the rectangular structure 1, 2, 3, 4 and so on. Then we get 28 nodes and 18 elements. Also we consider the third element. The node numbering is 9, 13, 14, 10. The maximum node number is 14 and minimum node number is 9. The difference is 14 minus 9 is equal to 5. We get shorter side numbering. The difference is 5. We know the condition maximum node number minus minimum node number is equal to minimum. So in longer side numbering we get 8 and shorter side numbering we get 5. So 5 is the minimum value. So we take the shorter side numbering in finite element method. The third step is selection of a displacement function or interpolation function. This involves choosing a displacement function within each element. It may be polynomial, linear, quadratic or cubic forms. For example, if a linear displacement functions, now in case of a one-dimensional problem, phi of x equal to a0 plus a1x. In two-dimensional problem, a0 plus a1x plus a2y. In case of quadratic polynomial, one-dimensional problem, phi of x equal to a0 plus a1x plus a2x square. Next step is define the material behavior by using strain, displacement and stress-strain relationship. This is the important word, strain, displacement and stress-strain relationship. We know the stress-strain relationship, that is sigma is equal to E into epsilon, or and the Young's modulus is equal to stress by strain. Or we know the other relation, strain is equal to change in length by original length, that is du by dx. We find the material behavior, define the material behavior. Next step is derivation of element stiffness matrix. Specify element stiffness matrix. That is F is equal to K into U. F denotes element. Nodal force is equal to element stiffness matrix into element displacement vector. We get the element stiffness matrix from three methods. First one is direct equilibrium method, second one is work energy method, third one is weighted residual method. In first method, that is direct equilibrium method, we take sum of the all the forces are in equilibrium, that is sum of force equal to 0, then we get element stiffness matrix. Second one is work or energy method. In previous semester, the advanced mechanics of solid subject, we study the minimum potential energy theorem and Castigliano theorem. Based on this theorem, we can find the element stiffness matrix in finite element equations. Third one is weighted residual method. Weighted residual method is a mathematical method. In this method, Galerkin approach is used. These are used in thermal analysis problems. The next step is step 6. In step 5, we get element stiffness matrix. This element, already in 5 elements, we combine these 5 element stiffness matrix and assembled together to get global stiffness matrix. That is, the next step is assemble the element equations to obtain the global or total equations. F is equal to K into U. F means global force vector, K is equal to global stiffness vector, U is equal to global displacement vector. The next step is applying boundary conditions. Finding the global stiffness matrix, we go through the boundary conditions. For example, if we consider a cantilever beam, one end is fixed, that is at end 1 U is equal to 0 and end 2 a force F is applied. The boundary conditions at end 1 equal to end 1 U is equal to 0 and end 2 F is force is equal to F, and then it is put into the global stiffness matrix. This is the step 7, applying boundary condition. And next step is solution for unknown displacement. U1, U2, U3 are the unknown displacements. We get these solutions from Gauss-Seidel method or Gauss elimination method. We already studied the Gauss elimination method in engineering mathematics. Step 9. Computation of element strain and stresses from nodal displacement. From step 8, we get the displacement values. After finding the displacement value, we also find the strain value. Strain is equal to du by dx. That is change in length by original length. Also find out sigma. or stress. Stress is equal to E into epsilon. E is Young's modulus. Epsilon is equal to strain. Next step and last step is interpret the result post-processing step. After the evaluation, the result is referred to as post-processing. The post-processor computer programs helps the user to interpret the result by displaying the result in graphical form. These are the steps involved in finite element method. These steps are very important. Next topic is application of finite element analysis. There are mainly two applications of finite element analysis are in case of structural problems and in case of non-structural problems. Structural problems includes stress analysis, stress concentration problems, vibration analysis, buckling analysis, etc. In non-structural problems means thermal analysis, heat transfer analysis, fluid flow analysis, etc. Next part we discuss stiffness matrix and shape function derivation. Thank you.